Last week, we have started working with monads. And monads are the top of the pyramid of the theory that we study in this course. Now we're going to start using them because monads are incredibly powerful and incredibly ubiquitous. Like, there are monads everywhere. In all the areas of programming, you might say, where we have some complexity and some heavyweight composition that play a role. We're now going to dive into an extension of the state monad, which is the state monad with errors and with suspensions and waiting. This state monad with errors and suspensions is called a coroutine. Coroutines are used to simulate threads, to simulate processes that are very long running, that can be interleaved with each other. Normal hardware threads, they just stop whenever the operating system or the scheduler of the threads decides, okay, you stop. But it could also be that a thread is not really supposed to stop, so the scheduler stops a thread and starts another one, and then the computation doesn't really mix correctly, and then you get so-called race conditions, like both threads read and write on the same variables, and then this can become very chaotic and unpredictable. Coroutines are controllable threads, where we specify exactly when the coroutine is allowed to stop and relinquish control so that another coroutine may resume. Multiple coroutines can run in parallel into different threads, so they can be mapped onto threads, but in general, coroutines are composable, and it's very clear how they behave with respect to state. We start with the definition of the coroutine itself. I'm going to start by defining a type which I call delta t, because coroutines run over time, and so they have access to how much time elapsed since the last time the coroutine woke up. That's useful for being able to wait and say something like wait 3 seconds, and you need to know that the 3 seconds have actually elapsed in tiny little bits. Delta t stands for delta time, so it's the difference in time, and yeah, I just give it a name because instead of number, this reads a little bit better. Then we will define a coroutine as a generic type that takes as input a context, a state, an error, and a result. You know what? I'm going to skip the error for now. This thing is going to be complicated, sufficiently complex already. And the coroutine itself will have, well, on one hand, the callable method, which takes as input a context, a delta t, and that's actually kind of it. And the context and delta t has type context and delta t. So the input that comes in the coroutine when we run it is, well, the current computational context, which will also be the input that will likely contain the state. We will see how to make sure that the context and the state are related later. We also simply say here that we get context and state. This would also be a possibility that we say that the context is whatever read-only context we want to provide, and also whatever mutable state we want to provide. And we pass the delta t because we need to know how much time elapsed. What do we return? We return a coroutine step, which we haven't defined yet, of context, state, and result. Okay. Of course, you might imagine, okay, what is this coroutine step? Well, the coroutine step is really the beating heart of the coroutine, because it says, okay, you've given me a context, and you've told me how long has it been since the last time you coroutine did something. And then the coroutine does whatever computation it's supposed to perform, and gives us back the coroutine step, which represents what the coroutine thinks is supposed to happen next. The coroutine step will always contain a new state. Okay, but what is contained in the new state? One might say, okay, the new state is going to be just a state. We're going to do better. We're going to say that what we expect is an updater of state. So the coroutine can stop, and when it stops, it will always give us a new state. But it's not really a new state, but rather a request to perform a change on whichever state is the latest state. So if we run two coroutines at the same time, and they both wake up and they both say, hey, here's the updater of the state, I can actually take these two updaters on the state that happen on two coroutines and apply both of them with the then method. So if I get two states, then I have two states, and how do I merge them? What do I do with them? I don't know. It's impossible to determine automatically, but if I get two updaters, I can merge them together by invoking the then method. We are going to see how this is implemented in practice. So I'm also going to say that a coroutine is allowed to signal that there is no change. So I'm going to allow the coroutine to give us a new state that could be undefined. There are many coroutine steps that follow each other in quick succession, and we want to be able to say that the coroutine has no update. Of course, instead of undefined, you could say that, well, we could have just given the identity. So the identity over state is kind of the same as saying, okay, there is no update. But we want to be able to skip having a composition of many identities, because even though it is functionally the same, this uses up performance. So this is an example where we are basically leveraging undefined to represent the identity, to avoid composing too many identities and skipping the useless compositions when a coroutine doesn't really have a new state for us. For example, a coroutine that waits for 5 seconds, it can say, okay, I want you to produce a new state with the identity, which is not going to change because it's just waiting. But it's also handy to simply have this coroutine signal properly, I have nothing for you to do, for performance reasons. Okay. Next to the new state, we always have a bunch of possibilities. And these possibilities we're going to put between brackets. The first one is that we get a kind result, and next to the new state, we actually get a result of type result. These two things together are very similar to what we had in the state monad, because if you remember, in the state monad, we had a function that takes as input here the state, which is in a sense our context, and gives us back a pair of the result and the new state. Here what we have is that we split the state basically in two, the part that we read of the state, which usually again is a superset of the state, so it contains everything in the state plus other stuff. Like imagine we're building a coroutine that interacts with, that defines an animation. So it is able to move some things around, move an object around. And this thing can also access, let's say, the username. So the username will be in the context, the position of the thing that is being animated will be in the context, but the state will only have the position because this thing is focused on animation and is not focused on changing the usernames. The username will be removed from the state, but available in the context. The coroutine, in one scenario, when we get a result back, gives us a new state, well, a state updater, but that is essentially a new state, and a result, just like the state monad. And this is where the identity between the equivalence between the coroutine and the state monad finishes, because the coroutine can also do other things. So the coroutine can also tell us that it is waiting for a number of milliseconds left. And after it is done, it will resume with a next coroutine. No, actually, no, that's it. We can simply say that the coroutine is waiting. Yes, let's keep it simple. And the coroutine can also be suspended. Yeah, let's call it suspended. And in this case, the coroutine can simply say, okay, I just want to stop for one instant. Like, just do the others that are waiting or suspended, and then come back to me immediately. And, well, obviously waiting and suspended are similar because the effect is that the coroutine is suspended in both cases, but suspended means stop me as shortly as possible, whereas waiting says stop me for a given interval of time. And the waiting means stop me until enough delta times have passed to cover the milliseconds left. And the coroutine, well, actually, that's kind of it, as a matter of fact. All right. So what do we do next? Well, we add methods to these things. So this coroutine, well, obviously we'll have a then method. We know how this works. We know how life works already. So we need map and we need then. Well, map is actually handy too. Well, then we want it in the coroutine. Map we can keep in the other place. So we're going to have to implement then here, because the coroutine is clearly very much like the state monad, something monadic in nature. The coroutine step, on the other hand, is it monadic? Maybe, but that's not that exciting. Most importantly, though, it is functorial. So we actually have map. So here for the coroutine, we will have map, unit, and join. And based on map and join, we will have the then method. And in case of the coroutine step, we will only have map. So you know what? Let's start with the coroutine step, because obviously the coroutine step is the smallest of the well, is the building block to define the map, unit, and join of the coroutine. All right, so coroutine step. Let's define our usual container object, which has to be generic in all the 3 arguments, and this will return all the methods and utilities that we want on the coroutine step. We start only with map, but this will clearly grow. So map will take as input the new result, calling it result1. Let's call it new result. I think it's a better name. Map of new result. And this will take as input f, which is of course, let me be consistent. Map, yes, it is as always a function, not a basic function. Okay, from result to new result. And this will return, of course, a coroutine step of content, state, because those don't change, and new result. Ah, of course. Wait a second. I'm having a very dumb moment. Okay, whatever. Cool. So, oh, well, of course, we also need to take. No. This is good. Then, well, this is what we return. But what I'm missing is the parameter. So we start with a coroutine context state and result. Yeah. Otherwise, so this is basically the this argument. So this needs to come somewhere. But when defining map as a separate function in a sort of a repository of operations like this coroutine container of operations, then the map function has the very beautiful formulation of take as input the lambda from result to new result and return the lambda from coroutine step of result into coroutine step of new result. So basically we're applying coroutine step inside the lambda inside the function on both ends, the input and the output of the function itself. Okay, so we return a function, of course, because we have to return this transformation coroutine step to coroutine step. We take the first coroutine step, which I'm going to very lazily just call underscore, and now we can start looking at the kind. Okay, so if the kind is result, then we need to transform the result. In order to do this, let me see how we did it for option. I just want to be consistent. So for option, we have this default object that contains the different constructors. So we're actually going to do the same. Default will contain one constructor for every one of these different kinds. it will always take as input the new state. So the first one will be, why is it unhappy? Because it's a function. Sorry, so I need the normal brackets, otherwise it doesn't understand that it's an object. That's why the compiler was behaving like strangely. Okay, so default result. This will define the constructor for the result. Now what I'm going to remove the result here, because the coroutine step is going to be fixed in the context and the state, but the result changes all the time. Okay, so result is generic in result, takes as input the new state constructor, returns coroutine step of context, state, and the result. And the coroutine step that we construct has kind, well, of course, a result in this case. The result is going to be, well, the value that we want to get, which we accept also as a parameter, and the new state is going to be the new state we received. I am aware that we are allowed to do this, so yeah, let's go for the slightly more hardcore version. Okay, then I'm going to finish the constructors. So suspended takes as input, well, only the new state. We don't have a result, and we simply change here the kind to suspended, and finally we have waiting, and this will of course be the name of this extra constructor. We get the new state, and we get the milliseconds left that we're supposed to wait. Okay, armed with this, we can finish the map function. So when the kind of the coroutine step of context state result is a result, then, well, we have a result that we need to transform in new result by applying f. So we call coroutine step of, well, context and state dot default dot result of, well, I'm just going to see if the thing can guess the result. I think it should be able to. F of underscore dot result, and the new state will be, well, what new state do we want to keep? Whatever new state we had in underscore, because there's no reason to break. There is no reason, of course, to break a new state. Whatever underscore wants to do to the state, it's its business. We only want to transform the result itself. Then, if the kind is suspended, there isn't much to do. We just create a new suspended version with just a new state. And finally, if the kind is, oops, waiting, then we create a new waiting. And waiting, well, how long is it supposed to wait? Well, exactly the same amount of time. Oh, and we don't need this check, of course. There is no check needed because the last case is always waiting. Okay. You could argue that waiting and suspending are semantically so similar that you could just drop suspended, and I wouldn't mind. Like, you could simply say that suspended is waiting of 0. So if you want to do that, cheers. I have nothing against. All right. Now we move on to the constructor, to the repository object of the coroutine itself. So coroutine of context state. Do we really want to have a default? Well, why not? Maybe we do. We'll find out later if we really want a default. But most importantly, we do need map, unit, and join. We start with map because, well, functors are nice, and they are, and obviously a monad is first a functor, and then a monoid. So we start with map because it makes sense. If we get stuck on mapping, then we have then we have a big problem. All right. So map also transforms the result, not the XPath result. Thank you very much, IntelliSense, for the help. I'm going to apply the usual copious amounts of laziness here, and simply change this into coroutine of coroutine step. Go becomes coroutine, and there we go. Okay, and now we can return a function. Oh my god, I apologize. Because, I mean, why on earth would we have curly brackets when we can turn it into a one-liner? I wouldn't really call this a one-liner. It's one expression, perhaps. You could argue that you could make it into a very long one-liner, but there is only so much evil that we can put into the world as human beings, you know. So let's be careful with this. Okay, now we return a function that takes as input our coroutine, and let's call it underscore. But now, what is underscore really? Okay, because indeed, like, so we have. Okay, so underscore is a function. So I can just call it and pass it a context and delta. I will get a coroutine step. The coroutine step is of type result. So basically what I want to do is I want to sort of, you know, call underscore. I don't really care about the parameters because the day will come. Like this coroutine that I'm returning is, you know, the usual synthetic proxy coroutine doesn't really exist. The only thing that this one does is it calls this, so this one gets a context and a delta t, passes it to this one. The argument is the real one that does all the work. This one simply calls the real one that does all the work, hijacks the result, applies f to the result, which is a coroutine step, and then returns whatever the coroutine step transformed with the result turned into the new result has become. So let's actually see how smart TypeScript really is. First of all, let's put the shut up compiler thingy. I'm going to say, okay, what if I say, well, it doesn't matter what it is, because underscore is callable, right? Underscore the coroutine is a lambda. This here is a function. So what if I pass it underscore? Oh. Of course. I have to construct this function in order to get access to this coroutine. So let's do it. Now, function underscore is now the actual coroutine. So inside this, let me kindly invite TypeScript to shut up. And here we see if I call fun of underscore. Underscore is callable. Underscore is a coroutine of context state result, meaning that it's a function from content delta into coroutine step. And FFF is a function from, context delta t into coroutine step. Oh, so you know what I can do? I can now say, well, call this, and then, okay, now what do we get here is a transformation from coroutine step context state result into, whatever, because until we specify which function we pass, there's nothing to do here. So I'm going to say, okay, you know what? Coroutine step of course, same context and same state, dot map. A map from result to new result. I pass f here. Okay, so pretty. FFF is now a function from context number into coroutine step of context state new result. It's very, very, very close to the coroutine itself. Now let's define the constructor of the coroutine. Default will take as input. Well, we generic in the result because we only have the context and the state, but the result comes later. Then we get this kind of function here. I'm actually going to simply copy this. Do we have the basic fun definition? No, we do not. No. We don't. We want the function or just a lambda? I think the lambda is a little bit better. Let's go. Well, this is of course the actual function. It takes as input a little bit of ugly typing. It takes as input something we don't really care about the name of, but I mean this is the argument we get, and it gives us back a coroutine step. Is it happy? Well, I don't know. And this is a coroutine of context, state, and result. Okay, at least there are no compiler errors. It's good. TypeScript at some point is very pessimistic when you're typing these longer things with generics. Like the whole line becomes a big red depressing squiggle, and you have no idea what is truly happening. Okay, but so here, well, we have the actual function, and now what we're going to do is we're going to say take the function. So const the const coroutine is equal to the actual function as coroutine. and then we return call. For now, there is no difference between the two. So we cast, and well, actually it's callable. Coroutine needs to be callable, and that's it. As soon as we add then here we will also have to do something like co.then is equal to, and then the implementation. If we only construct the coroutine through default, then we will not have to do any refactoring later on if we add then or even other methods. And this is just very handy and very comfortable. So here now we have this which is a function from context number to coroutine step. Okay, so we could even just say coroutine dot default of FFF. Well, I don't think this is going to work because it has no way to guess the types. Okay, and now I can start inlining things, and there we go. You know what I like about this? The density of information. It's like so many calories in one single bite is insane, but it's also like super healthy. Like there's no extra, there's no weight in there that is unnecessary. Like this is the most condensed, powerful information just in one expression. It is just beautiful. I mean, if you ask me, it's just beautiful. Maybe you have other words in mind than beautiful, but such is life. Okay, now we need to define unit and join. And I'm lazy, so I'm going to just say, okay, but well, what is this supposed to look like? And I'm just going to copy it. I'm just going to copy all these things actually. And well, I'm also very, very secretly, not secretly at all obviously, making the point of, remember guys and girls, that because these definitions are standardized, you actually get the luxury of just picking the structure of the implementation from other monads, and it always works because the structure is the same, the axioms and the guarantees that it needs support are the same, etc. And yeah, honestly, I like this. Honestly, I really like this because it really promotes not having to reinvent the wheel, and just already knowing that the interface is there, it helps a lot. Okay, so unit, what happens? Well, we get as input a value of type result. So this I'm actually going to make more explicit. So this is going to be function of a, which is our result. Okay, let's call this result first. We take as input a result, and we're supposed to return a coroutine of context, state, and result. Okay, well, of course this doesn't work at all, but that's okay. Yes, so we return a function that takes as input the value underscore because I really don't care. Then we call coroutine of context and state because I want to call the constructor, so dot default. And what do I give here? Okay, actual into coroutine step. And because we already have the result, we need a proper name for this. This will be the result, but what we pass to default, it gets as input the context and the delta t, but this we don't care about because we're building a coroutine that only gives the result back. So underscore, and now we have to return the coroutine step. Okay, so coroutine step of context and state dot default dot result of result and undefined because there is no state change here. And the compiler is even happy. Oh my god, I like this so much. Well, I also want to be a good Boy Scout right away. So why don't we say that we add wait? Because this makes a lot of sense. We do need, well, we don't have a result for wait. So the returning value will be unit. But what we do get is a number, a delta time even. We could say, yeah, we get a delta time. the delta time is a number, but I like giving another name to these primitive types like string and number whenever I want to convey the fact that, okay, they represent something more specific than just any number. So this is a time in milliseconds. We could even call this delta time in milliseconds, would be probably even more expressive. Okay, now, well, we obviously don't get the result, but rather we get the milliseconds left, and the coroutine step that we get is waiting for milliseconds left. And no state updater, because, well, we just want to wait. So there's nothing to do. Let's suspend. Well, suspend doesn't take anything as input. It just returns a coroutine of unit that is very simply a suspended coroutine with no state change. So these things are saying, okay, you can build a coroutine by simply saying, okay, here's a result, build a coroutine that just returns this result now. Then we can say, build a coroutine that waits for a given amount of time. Build a coroutine that stops immediately and will resume at the next iteration of the whole system. And there's another one that is missing, which I'm also going to add, which is a set state, why not, which takes as input an updater of state, and this will be next state or set state, whatever. I called it next state in the coroutine step, so I'm going to keep this this naming, and this will actually return a result, but instead of undefined, now we can actually put, oh, of course, unit and new state. So basically we can say, create me a coroutine that gives a result, that waits a given amount of time, that stops for one iteration, so it's like the smallest version of wait, that sets the state, and now we need to make it fully monadic, so we can construct it in all the ways. The reason why I just did all of this instead of jumping right away into join is that unit is one of the constructors, but if we have multiple constructors, multiple monadic constructors, I also like the idea of having all of them available. Okay, now, finally, well, let's rename this A to result, a little bit more expressive. Now, coroutine of, okay, so here we need a coroutine of context state, of coroutine context state, result. Ooh, this is very unencouraging. Wait, okay, I broke everything apparently. Ah, there's one too many, I think. Yes. Okay, so we have a coroutine that returns a coroutine of result, and we want to squish it down to a single coroutine of result. Okay, so now we take as input the original coroutine. Okay, and for this, well, this is the place where we actually need to do a little bit of implementation, because if you remember, when dealing with the join of the state, this is the place where we actually have to perform an honest-to-God implementation of, okay, well, how does the coroutine actually perform its transformation? Okay, so now first we start with getting as input. Okay, so we're inside the constructor, yes. So we're getting as input this coroutine of coroutine. All right. So we get the coroutine of context state result. And what we have to build out of this is the coroutine of context state result. So you know what? I'm going to just, because this coroutine is going to be an empty shell around this coroutine. So basically, whatever this coroutine does is running this coroutine, getting this continuation in the result internally, if available, and running that as soon as possible. So it's going to do this, yeah, this folding, this flattening in, so this nested execution. Okay, So I just return this new coroutine because it's a synthetic thing that I can just build, so I don't even need the curly brackets here. I can simply say, okay, fun. And this is the actual coroutine. Look, the signature of this is, okay, it takes the actual coroutine, and this actual coroutine is, okay, function that takes as input the context and number, and returns the coroutine step of result. And now we need to find a way to figure out how to build the coroutine step of result from the context, the number, and obviously the original coroutine, the nested coroutine P, which I'm going to call nested P and NP, nested program. Okay, so what do we get? Well, I get the context and I get the delta time. Now it is time to take stock of our options. Okay, now have NP, and I have, you know, the context and the delta t. I actually can call it. So I can say temp1 is NP of context and delta t. So we run, let's say, the outer shell. And of course, what do I get? I get a coroutine step. Okay, I get a coroutine step. So well, let's simply take a look at what's in it. So check the kind, and it could be that well, I get a result. So if I get a result, inside the result, what's in there? There's a coroutine, and I might want to run this coroutine. I can run it. Look what I can do. I can actually pass it the context. Do you know what? Let's do it. Let's pass the context. I have it, and the delta t. And well, this is going to be temp2. And okay, temp2 also can be something interesting. Okay, so let's take a look at what's temp2. Well, if it's a result, and now all of a sudden I actually have a result. I'm wondering if I can actually return temp2. Yes, the thing is happy. Why is it happy? Well, it is happy because this coroutine that I'm creating here, is supposed to return a coroutine step of context state result. So yeah, this temp2 is the coroutine step. Actually, I don't even need to check this. I can always just return whatever came out of just running the result, because in this case, yeah, we're done. So I can just run it. I can just return it. What about the other cases? And now there is a little bit more to it, because the types aren't really helping us. Because now what we do have, and this is one of the trickiest things when working with these coroutines. So what is happening here is that now I do still need to compose the changes in state, because temp1 wanted to perform a change in state, and temp2 also wants to perform a change in state. How do we deal with this? So, well, in temp2 I have new state, and in temp1 I also have new state. So I can't just return temp2, but actually what I should return is temp2, but the new state has to be the composition of temp1.newState, then temp2 of new state. What if they're both undefined? Well, then I get undefined. Okay, so let's define the new state as if temp1 has new state and temp2 also has new state, going to be very verbose here. If they're both not undefined, then what do? We do temp1 dot new state, then temp2 dot new state. Okay. Otherwise, well, okay, they are not both. They're not both defined, but temp1 is. Okay, then I return temp1 dot new state. Otherwise, I just return temp2 dot new state, which in this case might also be undefined. So new state could still be undefined. but it's an updater of state which is undefined. But if both temp1 and temp2 wanted to do a change transformation, a state transformation, then I concatenate them. And if only temp1 wants a state transformation, because if we get to this condition here, it means that temp2 is undefined. Then we just return the temp1 state transformation, otherwise we return temp2 of the transformation. And this case is the one that might still be undefined. In this case it isn't, but in this case, well, temp1 is undefined, temp2 might be undefined, or might be defined, but we just defer to that. Okay, now, so if temp1 is the result, great. Otherwise, well, okay, otherwise we have to check, because temp1.kind might be waiting or suspended, and the new state is an updated state. So actually here, I also say that we just return temp1, because temp1 already has the right shape. So now we know that temp1 is a coroutine step, and it doesn't mention the result, because the result we've managed already. Like if temp1.kind was a result, then we have to run the result because there is nesting there. But in all other cases, when we're waiting or suspended, there is no mention of the result. So actually, in this case, we can simply sort of flatten out the join, because the coroutine is just waiting. Okay. Now, well, let's take a look at whether or not we can implement then with the usual trick. So we have the initial, let's say, well, let's call these whatever, A and B. For the then operator, A and B are actually pretty okay. So we have a coroutine of context and state into A. We have a function then that takes as input whatever result came out of the coroutine and gives us a new coroutine of, as usual, context state and B. And, well, of course, we want to just flatten this, so we want to link the result of this with whatever f does, followed by a flattening. So let's see if this all still works. We can do coroutine of context and state dot map of an f followed by coroutine of context state dot I don't know why. I'm always almost surprised by this. Why would this thing work in God's name? Okay, amazing, just amazing. I mean, you can imagine how. I mean, join was tough to implement. Imagine implementing this from scratch. I mean, for optimization purposes, it's okay, but when you need to be live with a program like this, then that's it. It just works. Just works. Okay. Anyway, let's now extend the definition of coroutine with then. So let's say the two coroutines are supposed to have this then method. Of course, there is a complaint here because we aren't calling coroutine.default. It's okay. One step at a time. So we have, well, only the new result, because here inside the coroutine definition we already have a result, and well, this is going to be this, so we don't really carry it around. Result. The new result has to be explicit, and now we need to make sure that, okay, here we implement code.then, which is going to be a function that is generic in the new result, that has this as a parameter of type coroutine of context state and result. Then we get the f function, then we return the coroutine, and this is quite trivially returned coroutine of context and state dot then wants p and f. P is this, and f is f. Okay, this is happy. This one isn't happy, but I suspect it's going to be easy to fix. So we create the coroutine of context and state, and we just call default with the result of the function, because this basically just means that then is missing this function here wasn't a proper coroutine anymore because it was missing the then method. All right, it's kind of it. that is indeed kind of it. So let's define our program. Now, first I'm going to define a state. Oh, the state we have already. It's our oh cute. It's our memory state. So we already have memory. We're going to use memory as a state. Why not? Okay, so I'm going to simply instantiate this sort of coroutine repository with memory as a context and memory also as a writable state. Okay, then I can say co.unit, for example. You can say, well, please return a value. But you know what? I'm going to do some minor changes, because I don't like returning lambdas, because otherwise it's almost impossible to use these things. So I'm going to return the result right away. It's a little bit uglier, but it makes life a lot easier. So instead of the result, I just return the coroutine. I hope you're okay with this tiny step of refactoring. I just wanted to show that first we stick to really how these things are supposed to be, but then we also make them usable by sacrificing a tiny little bit of elegance. Okay, then here also we remove the extra function, because otherwise that double call wreaks havoc on the. Wait, did I break it? Oh yes, I did break it. On the type inference, and that we really don't want. Then suspend. No, suspend is fine, yes, and set state. Also here we get the updater of state directly. So next state is the updater. So just yeah, it's a pity that TypeScript is not a bit smarter about extending functions or having like extension methods in C#. So that's really a missed chance. I hope they add it at some point. Okay, so go dot let's say unit. I can say 10. Okay, and well, it's a coroutine. But I could say go dot set state. Okay, and do we actually have an updater of memory? Well, I really hope we do. Let me take a look. Oh, we do have this. Oh. Well, if you will forgive a moment. So memory. When we want to update value A, I'm going to get an updater of memory of A, which returns an updater of memory. And oh, brackets, brackets, brackets. So this will be a function that takes as input the current state and returns instead of A the value of calling underscore over current dot A. So this just applies a given transformation onto A, and I'm going to have 4 of these: A, B, C, D. If you're wondering whether or not this could be automated or streamlined, you're wondering right, because the answer is yes. But if you're wondering why I'm not going to do it, it's because, yeah, I mean, I don't want to kill myself, actually. I'm being careful with my own mental energy. So for now, I'm going to go for a little bit of code repetition in an array that's easy. Why did I do this? Well, because set state now wants an updater of memory, and I can say memory dot A of, and then, oh, do I still have incre? Oh, I still have incre. Well, how about this? Increment A. Okay, then how about also increment B? Why not? But you know what? I don't want to increment B directly. Oh, of course, this would be then, and set state doesn't really give us much to work with. So I mean, it gives us a unit that we can safely ignore. Okay, and I could say, before doing this, how about wait for 2.5 seconds, and then set the state. Now, how are we going to run this? Oy, oy, oy. Now, well, how about we turn this into something that we can reassign? Then do while true. Do while true. We need a current memory. But what values did we pass to the example here? Oh, we just created it like this. Okay, current memory has type memory because we need an initial context, of course. But we also need to be able to adjust it. Let's say then the delta t, we pretend that every tick is taking 10 milliseconds. Actually, we should have a proper timer, but for now we don't care. We will actually see how to put a proper delta t later in the next lesson when we introduce the React renderer of this. Okay, so, well, let's call p on what? Well, it wants a context and a delta time, and it gives us a step. Very good. Oh, pardon, context, current memory, of course. And then the current memory might change. So we say that the current memory is going to be, well, first we check if new state is not undefined, because if it is not undefined, well, we call new state on current memory. Otherwise, we just keep the same current memory. Okay, this is an assignment for nothing, but this is, yeah, okay, I could also say, let's skip the assignment for nothing, why not? Yes, oops, there we go. All right, so if the coroutine wants us to perform an update on the state, then we perform the update on the state. Okay, and okay, but here's the slight challenge though. Okay, so the coroutine can say that the kind can only be, so let's take a look at the kind. So, okay, so if we're waiting, then, well, there's only a bunch of milliseconds left. Okay, so how about then we need to wait. All right. Okay, so if we're waiting, we have to check if the milliseconds left are smaller or equal than the delta t, because this means that, well, we're done waiting. So in this case, well, the whole thing is over, even though, unfortunately, yeah, we will need to perform an extension later on. So in this case, well, there seems to be nothing to do, because the wait is over. Otherwise, we can reassemble the coroutine by saying that p still has to wait. So our program has to contain a waiting that is decreased, where the milliseconds left are decreased by the delta t. So we're going to create a new coroutine, in this case, well, of memory and memory, because these are the context and the state. And then we create, wait a second, oh, sorry. Oh, no, we don't need to specify it because it's already there. So we create, a waiting coroutine with milliseconds left being equal to step.milliseconds left minus delta t, because we still have to wait, and so the external loop still has to do some waiting. Okay. Otherwise, and so otherwise, in this case, it looks like, okay, the coroutine has yielded. So if step.kind is suspended, then, well, there seems to be nothing to do. And finally, the coroutine has actually returned something, so we can check no, actually we can check here, step.kind is a result, and we have the result, but we know that the result of this particular coroutine is going to be unit, so we can just safely ignore it, or we could just print, okay, the coroutine is really done. So here we're actually going to return, so that we can, no, okay, no, we are not going to return, we're going to have a flag running, which is true, and then we put the flag here while running, and here we say running is equal to false, because the coroutine has finished. Okay, all right, so the thing that I would like to discuss with you guys is, okay, so this implementation is a start, but it's still broken, it's still not what we want. So, okay, what is the problem? The problem is that you can see that if this thing is waiting, then where is the rest of the computation? So what happens to the set state that has to be performed as we get into the wait? Now, let's take a look actually at join. So if this, because the waiting will always be hidden. So the waiting will always be hidden in temp1. So in the coroutine step, what we can do is we can actually extend the definition of the coroutine step and also of suspended in order to contain whatever next step the coroutine is supposed to perform. So now in next, I'm going to accept a full coroutine of context, state, and the result. Okay, so because what are we doing here? We're saying, okay, a coroutine can wait or can be suspended. But if I say that a coroutine is a coroutine or a coroutine step that is supposed to return a result, then it's supposed to eventually return a result. And if it is suspended, we cannot simply say, oh yeah, you're suspended, so there is nothing left to do. That makes no sense, because eventually we need even a waiting or suspended coroutine to be able to produce a result. So here, what we stated was, okay, the coroutine step can be a result, or it can mean that the thing is waiting. Okay, but if it is waiting and it promises me that it's going to give a result back, so I need to be able to call the function f of the then. So the result needs to come at some point. We're going to extend waiting, but we're also going to extend suspended, because in both cases we need to know what comes after this coroutine. Okay, so of course now when we created the coroutine step, so we haven't changed the coroutine yet, but the coroutine step itself, we do need to be able to state that, okay, this thing is suspended, but we also know how it's going to continue in order to produce whatever result we wanted. And indeed, you can also see that we have this result type argument, but there is nothing that guarantees that the result is coming. So next, and next. Wait, oh, okay, it's happy. And here waiting, okay, wait so much, wait so long. When you're done, this is how you produce the next value. And there we go. Okay, now, so a few things are broken, well, we can see obviously. Well, everything is broken actually. But the thing that's the most broken is this one now, because if we're suspended, well, now we need to create a new suspended, and we need to provide a way to move on to the next computation. But this way to move on to the next computation, okay, so here in suspended we need to return it for new result, but what we have is the one in underscore that is for the result. We have next here, which is a coroutine. I need to transform this coroutine so that instead of being a coroutine of result, it's a coroutine of new result. So the coroutine maps the coroutine step inside it, but the coroutine step inside it, if it's suspended or next, has to map the coroutine. So they are mutually recursive. Let's make it mutually recursive and let's see how far we come. So coroutine of context and state dot map of f. F will map result into new result of, and here we have to pass a coroutine of context state result, which we have because it is next coroutine of context state result. And is this happy? Well, I don't know. If it doesn't work, you know the drill. And here we're also missing next. Oh, it does work. But it also makes perfect sense. Like, why wouldn't it work? Okay, cool. So now we're making sure that the way to calculate the value after waiting and after suspending has been embedded into the coroutine. Okay, cool. Now, of course, this is very broken. This is a little bit broken. For the step that we take when waiting, here, actually, this wait can actually accept a coroutine of context state dot unit of nothing. This is actually fine because here we're simply saying, okay, we just want to create a coroutine that waits, and then we'll not lose whatever else we do after then. So don't worry about the fact that we don't need to put the next coroutine in these constructors, because the next coroutine is only relevant to make sure that whatever we passed to then, or actually this f function here, doesn't get lost when we do actually this map here. In this mapping, f needs to be called eventually on the result, on suspended or on waiting. So that's what we need to do. But here, when we're simply saying wait, well, we need to create a coroutine step with waiting, but this is not the f that we really care about. It will come later, as long as that f is embedded. And now we have to embed that f somehow. Okay, and now the tough one, the terrible monster. Okay, now it gets real. Just a minor note. I'm trying to go slow, I'm trying to explain everything, I'm trying not to get excited, but my heart rate is accelerated because this is genuinely scary. Okay, so, well, I'm guessing that these are the bits that are screwed up. Okay, well, I was guessing right. Okay, so here we have our result. Wait a second, this isn't screwed up. This is okay, actually, because in this case, okay, so temp 1 is a result. So inside of temp 1 we have, well, the actual nested coroutine. We start that coroutine and we compose the state transformations that are desired. So this is covered. Okay. In this case, on the other hand, well, we have two states, and I think we have to manage them both separately. So if temp1 dot kind is waiting. Okay, what do we have here? Okay, here we actually have the milliseconds left. Okay, so this we don't really touch because it's not up to us to actually do this. We have the new state, and we have next. Let's take a look at next in particular, because next is a coroutine of context state of coroutine context state result. Okay, and what we want to return, so now we can't return temp1 like we did before, because this temp1 has the wrong type, because temp1.next is not what we want. So what we're going to do is we're going to say, okay, what we could return is coroutine of context and state dot default. Then to this, so we have to create something new that behaves like temp1, but which actually has the next value that we really need. But wait a second. So, and this next value will have, again, well, it will have kind waiting. It will have the same milliseconds left. It will have the same new state, but this next here is the result of joining. So this next here, which is a coroutine of context state and then coroutine of context state result, this actually has to be squished down. So let's say next joined is going to be temp1 dot next. Well, I wonder, can we join this? Let's see if we can join it. Perhaps we can actually, because this is a coroutine of coroutine, so perhaps we can actually join it. So coroutine of context and state dot join. Oh, and let's see. So the next join is now a coroutine of context state unknown. Okay, because you're of result, and it is happy. This is type safe. Okay, so next joined. Oh, I wonder if we can just simply say return temp1 where next is equal to next join. Is it happy? It is not happy. Well, now let's hammer next joined into temp. So what if I stated, because I need to return a coroutine step now. Well. Okay, coroutine step of context and state, not default, not waiting. Then we get temp1 dot milliseconds left. Next joined should actually be the right one. The new state will be temp1 dot new state. And is it happy? It is happy now. It's a coroutine step of context state result. Can I just return temp2? Wait a second. What is happening here? Oh my god, because we call join itself, and so this function, so it doesn't know what this function returns. Okay, yeah. I'm already anxious enough about this whole thing. Come on, TypeScript. And this will return a coroutine step of context state result. Okay, very good. So if we're waiting, well, what I'm doing is I'm simply saying, okay, then fold the next, because there is the next thing which also needs to be folded, and then just return the coroutine step that waits. The last case is going to be almost identical. This code does need to be cleaned up at this point. Obviously, this is not going to be waiting, but this is going to be suspended. There is no milliseconds left, there's only next joined and then temp1 dot next state, and this return now doesn't happen anymore. Okay. Still, it looks like we are missing something. Does it do? No. Well, what are we missing now in the runtime? This is not correct anymore, because if the step.kind is suspended, well, what do we do now? We say that p is equal to step.next. And of course, the same applies to whenever the step is finished. This one, on the other hand, is not correct. So because now step has next in all waiting cases, and here what we say is, okay, you're supposed to wait a bunch of milliseconds left, and you still have some time to go. So okay, we reconstruct basically the coroutine by saying, okay, wait whatever you're supposed to wait left, but don't forget that after this you have to continue with step.next. And I don't want any weird closures to screw up our fun. And now next is a coroutine of units, so because otherwise we forget it. And now you see that 0, 1, C, and D. Let's restore the code to set state. And now you can see that first. Okay, so what is happening? Okay, so we're about to run an iteration with 0, 0, C, and D. That's the initial state. The first thing we do is we increment A. So we get A1, B0, C, and D, and now we're waiting. And there is next. It's very important that now we get next. What is contained in next? This is contained in next. This whole thing is next. Okay, so the wait kind of bubbles in front of us, and the increment of b is the next bit. Then we wait, and there's nothing to do in the next state, in the new state. Here there was something to do in the new state because this was the increment of a, and then when we land in the weight 30, there is still the increment of a to do, so we do it. And then this is the new state, and now we wait 10 milliseconds, so we have to wait 20 more. And there is no new state, but there is still next, because we still need to treasure the fact that, okay, this is how the program continues. That's the whole set state. So we do this 3 times, and now you can see, okay, the last bit, we still have next, and then the iteration has finished with a new state, but the kind is result because now we're finished, and then we have A1, B1. So the set state of B incre has been run. Then, let's say that we wait again. Did I kill a bracket? Possibly. We wait again. Well, 30 milliseconds, why not? And we increment A again. And that is it. Okay, wait. What did I do to the brackets? Okay, this bracket, this bracket, this bracket, this bracket, and this bracket? No? Okay. Alright. So then we increment A again after 30 milliseconds. So now you can see, well, obviously these are not actual milliseconds because we're simulating them, and obviously this while loop is very quick. And now you can see that we wait 30, 20, 10, 0, and now B has been incremented. The increment of A worked already, and then we start to wait again. 30, 20, 10, and now the result, and A is 2. So, I don't think we're entirely done. I want to show you something else. Now we open up a world where we can do so many new things. We can run coroutines in parallel, which is the next thing we're going to do. We can run them in sequence, because yeah, this is kind of a sequentiality. So how about we make it more explicit that we can do things in sequence, and so on. I'm going to show you 2 operators that make this even more beautiful. The first one is the sequential operator. Sequential operator takes as input an array of coroutines of a given result that we don't really care about. So it takes as input, well, P is programs, or yeah, programs, whatever. There's an array of coroutine of context, state, and A. This gives us back a single coroutine of context. Yeah, thank you. Audio context, of course. Context, state, and unit. Alright, it is happy. And yeah, this one is super easy, because what we do is we say, okay, if piece.length is 0, there's really nothing to do. So I can simply say, okay, you know what? I'll just tell you immediately that this is a coroutine of context, state, unit, no, sorry, context and state, dot unit, and then I just pass it unit. Alright, so if you give me an empty array, running an empty array in parallel simply means that you get the result. There you go. Otherwise, I run the first one, and well, it's a coroutine, so I can simply say then. I ignore the result because I don't care, and say, well, how about please you run me in sequence context state dot sequence of oh, wait a second, oh my god, ps dot slice starting from 1. Yes, okay, So this says basically take everything after the first element. And what we are able to do is, instead of using then this much, because then is kind of ugly to use, I can say, okay, but because these things don't really care about each other, so I can say, okay, set state, and followed by wait, followed by another set state, because unless you use then when you really want to read the value that came out of a coroutine into the next one. But if you just want to say run them one after the other, then you can use code.sec. Let me check that we haven't screwed it up. No, you can see, oh, chew, 1, C and D, and we have the double wait. Yes, you can clearly see the double wait because this starts at 30, waiting to increment B, then B gets incremented, we start again, and then we increment A for the second time after the second wait. Let's, well, we can play around with this for 5 minutes. Come on, after so much pain, let's enjoy ourselves a little bit. Let's define get state because, well, it is super useful, or yeah, get context actually. Let's call it get context. Get context does give us a coroutine of context, state, and context. So the value is undefined, and actually here what we create, well, we don't give unit as a result, but rather we give underscore of 0, which is the context. And now what we could do, okay, here we're incrementing, but what we can do is we can read the state. So I could say that before waiting, I get the context. This gives me the current state. Let's call it current mem. Let's call it context or whatever. Who cares? And then I wait based on, well, I don't know, 30 times context dot a, which I read from memory, right? So this is so set state changes the state, but sometimes you want to alternate reading from the state and, of course, writing to the state. And I could even say that in the memory there is extra information, like let's say the authentication headers, for example. I mean, who cares, right? And I put the authentication headers here, and this will be okay. Let's give it a name. Type context, and this is memory and this authentication string, so I can say the current memory. Yes, this is memory, but here in the step I'm passing, I need to pass both the memory and also this the extra data, like the authentication headers, blah blah, super secure. Okay, so now get context has access to more information, authentication headers, for example. In this case, you could check, okay, if you're logged in, wait for 30 milliseconds, and if you're not logged out, wait for 3 seconds, because you need to wait for longer. I don't know, doesn't make any sense, but the set state only works on the memory. And I'm just saying this very quickly, but actually this is a very important pattern in managing, in merging software engineering in practice with the theory from category theory. It's also learning how to define components that operate just on that can limit writing, especially. That's like the core trick. You don't want to be able to write on everything. You just want to write on a smaller subset of the whole state. So you could say that this is actually the state because it has more things, but we define a coroutine that can only write on a scope, a subset, a specialized subset of the whole state, so that not every coroutine gets to read and write to the whole state, because otherwise things get very, very messy. So we have this, and the last one I want to show is any. Any is also insanely powerful. Any takes as input an array of coroutines and returns a coroutine that triggers with the first of these that gave us a result. Basically, it's a way to say run these things concurrently. Run them like in a race against each other, and whichever terminates first, that's the winner. All the others, we stop them. This is the key to well-behaved concurrency. And also notice that it's kind of like we're saying that an array of coroutines can be embedded in a single coroutine. It's kind of almost like a flattening. But we know array is a functor, coroutine is a functor, and we're saying that array and functor together can be embedded into, sorry, array and coroutine together can be embedded in a coroutine. It's kind of almost like a join, but with a sort of slight asymmetric twist. Okay, so there will be more to say about this later. Okay, so what we're going to do now is, well, we're going to define this coroutine because this is what we need to return anyway. So actually I'm going to take this coroutine and I'm going to create it. So now we really need to manipulate, like any is a very low level operator. I get the context and the delta time. I actually need all these things. And here, well, I have this this array. Okay, first of all, let's get the compiler to chill a little bit. Okay, so now what are we going to do? We're going to give a crack at every one of these coroutines. But if one finishes, it's great. Then we stop, we have a result. But in the meantime, all the changes in state that they want to perform, we have to concatenate them together. So we will carry with us the new programs, which is going to be an array of coroutines, and we start empty because these are the ones that are coming back in a sense. All right. Then we need the next state, which is going to be, as you can imagine, an updater of state or undefined. And this starts undefined. And these are the accumulators that will carry with us whatever the next step is supposed to be in case none of the coroutines have terminated. Okay, so now we can finally run them. So we take PS and we iterate, and for every one of these coroutines, I take the step, the coroutine step that comes out of it, and I simply take P and I call it with what? With the context and the delta T. Okay, and I check, because if the step is a result, well, then we're done. I can simply return coroutine of context and state dot default. Oh no, sorry, I return a coroutine step dot default dot result, because we're done. What is the result? Well, the result is whatever came out of step. But the new state is not whatever came out of step, because there are next states that might have combined from all the coroutines that we ran, all the other steps that we ran until now. So now we have two things that we need to join, and I'm actually going to copy it because there was this thing where we took the two possibly undefined states. Where was it? Oh, here. Okay, so we're actually going to turn this into a little function that is a sort of then, but let's say then maybe, which takes as input A, B, and C, of course, a function. You know what? Let's just turn it into an updater, because we know these are updaters. So an updater of S or undefined. The next one is updater of S or undefined, and this returns. Is it happy? Yes, it is happy. Okay, and I can just copy this. I can say, well, if F is not undefined and G is not undefined, okay, then I can just compose them. I can simply say F, then G. Okay. Otherwise, if only F is not undefined, I return F, and otherwise G, which might be undefined, but in that case, well, if G is not undefined, we get G. Otherwise, well, we still get G because F is already undefined. Okay, so we have this then maybe. we can actually say that new state was then maybe of temp1.nextState and temp2.nextState. So we clean up a little bit. That's always nice. And also here, because as next new state, I can say that here I wanted then maybe of next state, and also step dot new state. Oh, pardon, next state. We call this new state. This thing is complicated enough if we are consistent, so let's make sure we do it. And because we are going to have to do this anyway, let's say that we always say that new state carries with it whatever the next step wants, so that because we still need to update it for every case. Okay, so here the step.kind is a result. Okay, there's nothing to do. Otherwise, well, we have taken a step. So the thing that we carry is next, because the suspension and the waiting, they both have the next, the continuation. And this continuation we put in new PS. We say, okay, so we are not done. Great, so we push a coroutine of context state away, which is step dot next. So we are rebuilding the array. And we're accumulating all the changes in states because we build the array by triggering all of them. If at some point we finish, then we take all the new states, we have combined them together, and those are simply given back together with the result, because otherwise we discard a step. And otherwise we rebuild the array with all the next steps, and at the end, what do we do? What do we do? Well, we call, okay, we could say we call set state because we have a new state. But what if the new state is empty? Well, I'm going to be lazy for a second, but so, oh, why is it not happy? Why are you not happy? Oh, because it's not coroutine. Coroutine of context and state. Dot set state. Okay. Oh, no. Again, because we're inside the coroutine, so we take the coroutine step, and we are going to create a coroutine step, which which suspends once. Next is going to be, well, we still have all the new PS to run, so it's going to be coroutine of context and state dot any of the new PS. And what is the new state? Oh, it's quite easy. It's just a combination of the results of all the new states. What does this operator allow us to do? It allows us to do things in parallel. So I could say that here I want to run two things in parallel. I want to run both A. Oh, why is it unhappy? Why? Oh, okay, it isn't unhappy. I want to increment A and B. Any is a special combinator because the idea of any is that it runs the coroutines, and running the coroutine is something that doesn't really belong to the coroutine. It's something external. So this logic of take the next step, but this logic has to take care of whether or not we are waiting, suspended, or in a result state, and this is the running of the coroutine. And this logic has to be embedded inside any. So any is, in a sense, handy to treat it as if it were part of the coroutine, but actually it's a coroutine runner. It's a special runner of a coroutine that can also run that returns also a coroutine. But what it does is it runs the coroutine. What we had so far was an any that sort of skips the waits. And that's kind of unfair. So what any does is for every coroutine in the array of coroutines that we have to run concurrently, well, if the coroutine is done, great, then we return the result that the coroutine gave us with the concatenation of all the state transformations. Otherwise, we go to step.next. What's missing here is that, well, we actually have to check whether or not step.kind is no stereo pender mode. What would stereo pender mode even mean? Come on. If step.kind is, okay, this can be either waiting or suspended. And if we're waiting, there are actually two things that we need to look into. So if we're waiting and the milliseconds left are greater than the delta t, it means that we took this instance of the coroutine PE, we ran it, but now what we push into the next step will still be waiting, but, well, without the delta t. Like, we had to wait 100 milliseconds. Delta t was 10, so now we have to wait 90, which is 100, that is ms left, minus delta t. Okay. So what do? We do new PS, so the next generation of the coroutines to run, of course, dot push, and here we say, okay, coroutine of course, context and state are the same. Then we wait for step.msleft minus delta t. But after we waited, well, we're still supposed to do whatever step.next was expecting of us. Because, well, the coroutine step says, okay, I have to wait for 100 milliseconds. Okay, great. And then in step.next, we find whatever was supposed to happen after the wait, and we don't want to lose step.next, so step.next remains exactly the same. Okay. The other scenario, which I'm going to lazily copy, is, well, if step.kind is waiting, well, we could say, just to make this very explicit, and step.milliseconds left is smaller or equal than delta t, but this is implicit. So, well, I'd rather not repeat it. And here, well, we don't really wait, but what we rather do is we suspend. Because if someone says, okay, wait 5 milliseconds, so they expect the coroutine to still take a break, and the delta t is 10 milliseconds. Okay, so what do? Well, we can't really run and not run the next step, so what do? We simply say, okay, well, we suspend for just one iteration, and then we run step.next. We could also say step.next. This would be a little bit less conservative. You know what? I'm going to leave both of them, and we will play around. We will decide which one we like the most. Actually, I think this is interesting, by the way, but it is a little bit more dangerous, because if the delta t step is too big, then you might completely, now you will not really skip, because this iteration of the any has already taken the step, and step.next will happen later. So we could also say that this is a decent combination. Okay, and if step was suspend, it's okay, because we are per definition suspending. So that's cool. We just put a step.next. Okay, I will leave this else if, because we might want the ability to restore the other situation. Maybe one could even make it configurable. Okay, now we get to test this. So I will take our coroutine, and how do we test this? We're going to test this in the simplest way I can imagine. So we're going to take any, well, any was the bit that we still need to change. Then we can say, I'm going to take this bit here. Okay, what does this bit do? This bit is one of the two branches of the any. It increments b. I'm going to let this wait for 100 milliseconds. The delta t, I'm going to make it smaller, higher resolution steps, 1 milliseconds. Well, obviously delta t should be calculated based on the actual speed of the machine, but for now we're not really caring. And what we do here inside the any, let me define something that increments. Okay, something that performs this this increment logic, but then on a with intervals of 10 milliseconds. So increment a forever, and after having incremented a and waited for 10 milliseconds, we are going to increment a forever again. This is probably complain. I'm not even going to check. It's certainly going to complain that it can't guess the type, because increment a forever is calling itself, so it's just guessing any. So I'm going to also say that the co-type of result is coroutine of context memory result. So I can lazily simply specify co of unit. And now increment a forever is happy. Okay, and here is the first branch of the any. I just increment a forever. Okay, so what is this thing doing? Well, it's incrementing a forever in steps of 10. And here we increment b. You know what? Then wait 100, then increment b again. Okay, so let's run this. Okay, now this actually looks pretty good, right? Because what is happening? Looks pretty good. This is a friggin' understatement. So A has been incremented. You can see all the increments, and you can see there's many steps because now the delta t is tiny. So there's many steps in the delta t that just run this weight. So in order to run this weight, you need 10 or 11 steps. Well, let's take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 steps with a equal to 7. So for a to go from 7 to 8, well, there was a weight 10. So this took 10 increments. Okay, but then also, how many increments do we have of a? We have 10 increments because we started at 0, and if we perform the increment 10 times, we land at 11. And also b has been incremented twice. I mean, and also I could say, well, you know what? How about I want to increment b at smaller intervals? Well, there you go. And a is still 11 because we did the 10 increments. This thing is insane. Like, now you should be able to see the power of simply controlling time, controlling how computations happen over time. We have this repeat thing that takes as input a coroutine of unit, and what it does is it runs p, it runs a suspend, and then it calls a repeat of p again. So basically, well, it does one instance of p and then one suspension. And the suspension is to make sure that we suspend. So even if p does a wait, basically we add one extra suspend just to be sure. I'm wondering if we actually can just call a repeat of p like this, or this gives a Stack Overflow. Let's see if we get lucky. If we don't get lucky, then we're going to adjust this later. No, but I don't like to, I don't like it. No, I don't like it yet. What I want to do certainly is to make, because this is way too risky, just calling repeat of p immediately, this cannot possibly work, no. So what we're going to do is we're going to say, okay, first, oh, and I'm also going to make p lazy, because I think this will work better. So in order to make this better, I want to have the repeat of p, this recursion, to really be hidden in the closure of then. I don't, because this way, what we pass to then is this lambda. And this lambda will call repeat, but we don't try to call repeat immediately to create the coroutine. Otherwise, this tries to create a sequence inside a sequence inside a sequence forever. I think this is a little bit safer. Okay, and this increment a forever, well, this increment a forever basically will do this without this ugly recursion. I simply say co.repeat. This has to be a lambda into the body. So we've made the body sort of lazy. I noticed that, well, we don't even need to give a name to this because, well, it also fits in line. It's very cute because now we can build these combinators like repeat, even build something like while, and, oh, wait a second, yes. And they should allow us to basically define a sort of mini programming language. But first, a moment of silence and focus. Yes, it works. You might wonder, oh, wait a second, there's one increment less. Yes, there is one increment less because after the wait we have a suspend. So this is forcing us to lose a little bit of time. I'm wondering if I put 9 here, we get back to 11 because the delta t is 1. So by taking a step of 9, wait basically does 9 suspends because every suspend is equal to 1 of these fake milliseconds, and then the extra suspend that repeat added adds the 10th step. Or one could say, you know what, if you're using repeat and you're not a psychopath, then yeah, the body of the repeat should contain already a suspend or a wait, and if it doesn't, well, sucks to be you. And in this case now I restored, as you've seen, I've restored the 10, and now we get again the 10 updates that we wanted. And this kind of concludes our arch of coroutines. I can imagine that this is a very, very tiring lesson. This is the most difficult topic that we're going to touch in the whole course. I think the next one is going to be a lot easier. So, well, my thanks for the, hopefully holding on until now. And the best of luck with getting through this thing. Cheers. So, talk to me. Come on, guys.